Welcome! In this session, we'll explore an interesting problem titled Smallest String Starting from Leaf. Together, we'll break down the problem, understand the intuition behind different approaches, and analyze their complexities. Let's dive right in. In this problem, we are working with a binary tree where each node's value represents a letter of the alphabet. Specifically, the value 0 corresponds to the letter A, 1 corresponds to B, and so on up to 25, which represents Z. Now, the key idea here is that each leaf node in the tree forms a string. This string is constructed by tracing a path from the leaf node back up to the root of the tree. For example, if a leaf has the value 1, corresponding to B, and its parent node has the value 0, corresponding to A, then the string for that leaf would be BA. The task is to find the lexicographically smallest string that can be formed in this way from any leaf node in the tree. Remember, lexicographical order is essentially alphabetical order, so we are looking for the string that comes first alphabetically. The output of this problem is a single string, which is the lexicographically smallest string formed by any leaf-to-root path in the binary tree. Let's consider an example to understand this better. Imagine the input tree has nodes arranged as follows. The root node has a value of 0, which corresponds to A, and it has two child nodes with values 1 and 2, corresponding to B and C. Each of these child nodes has two children of their own. When represented as a tree, the nodes form a structure where the root A splits into B and C, and each of those splits further into D and E. The strings formed from the leaves to the root are DBA, EBA, DCA, and ECA. Among these, DBA is the lexicographically smallest string, so the output for this example is DBA. Here's why DBA is the smallest string. Starting from the leftmost leaf D, the path to the root forms the string DBA. The next leaf, E, gives the string EBA, and while it shares the same root, it comes later alphabetically than DBA. Similarly, for the right subtree, the leaf D forms the string DCA, and the leaf E forms ECA, both of which are alphabetically larger than DBA. Now let's look at another example. Suppose the root node has the value 25, corresponding to Z, and it splits into two children with values 1 and 3, corresponding to B and D. Each of these has two children, forming a tree structure where the leaves correspond to B, D, A, and C. For this example, the strings from the leaf nodes to the root are BBZ, DBZ, ADS, and CDZ. Among these, ADS is the lexicographically smallest string. Notice how ADS comes before BBZ, even though B is earlier in the alphabet than A, because we compare the strings as a whole from left to right. This highlights the importance of considering the entire path, not just the leaf value. In another example, the tree is structured such that the root has a value of 2, corresponding to C, and its left child also has a value of 2. The right child has a value of 1, which splits further into a node with the value 0. When tracing paths from leaves to the root, we construct strings like ABCC and ABC. In this case, the lexicographically smallest string is ABC. It is smaller than ABCC because, while the first three characters match, ABC is shorter, and shorter strings take precedence when sorting alphabetically. This example introduces another layer of complexity, emphasizing that not only the characters but also the string length impacts the result. Moving on, let's discuss the constraints of the problem. The number of nodes in the tree can range from 1 to 8,500, meaning the solution must be efficient even for large trees. Each node's value is between 0 and 25, corresponding to the 26 letters of the alphabet. Finally, let's consider some edge cases that you might encounter. For instance, what happens if the tree has only one node? In this case, the output will simply be the letter corresponding to the value of the root node, as there are no other paths to consider. Another edge case is when all leaves produce the same string, meaning the output will be that common string regardless of the tree structure. Additionally, in a tree that is completely skewed, where each node has only one child, the single path from leaf to root will determine the output. Lastly, there could be a scenario where the smallest string comes from the longest path in the tree, so it's important to account for all possible paths when solving this problem. To tackle this problem, we first considered the brute force approach. The basic intuition here is to generate all possible root-to-leaf paths in the binary tree. For each path, we would construct a string by working backward, starting from the leaf node and appending characters corresponding to the node values until reaching the root. Once we have these strings, we compare them to determine which one is the lexicographically smallest. The process involves a depth-first search, or DFS, to explore all paths in the tree. As we traverse, we track the smallest string found so far using a global variable, updating it whenever a smaller string is encountered. However, while this approach is straightforward, it has notable inefficiencies. Constructing strings for each path is computationally expensive, particularly for deep trees, and the time complexity can grow to n squared in the worst-case scenario. For a tree with a height equal to its total number of nodes, this becomes prohibitive. Additionally, the space complexity is h, where h represents the height of the tree, due to the recursion stack. Overall, this brute force approach is simple but not optimal, especially for larger or more unbalanced trees. Now, the optimized approach builds on key observations that help us avoid the inefficiencies of the brute force method. The main insight is that we don't need to construct and store all strings explicitly. Instead, we can compare paths lexicographically during the DFS traversal itself. By maintaining the current path string as a stack or list and updating it dynamically as we traverse, we eliminate redundant computations. The optimized strategy involves three main steps. First, we use DFS to traverse the tree, and at each node, we prepend its corresponding character to the current path string. Second, when we reach a leaf node, we compare the current path string with the smallest string recorded so far and update the smallest string if necessary. Finally, we backtrack to explore other paths in the tree. This approach reduces the time complexity to n, as each node is visited only once, and string comparisons are minimized by leveraging partial paths. The space complexity remains h for the recursion stack. While we considered alternatives like BFS or iterative DFS, BFS is less memory efficient since it requires storing all nodes at the current level, and iterative DFS adds unnecessary complexity without significant benefits. The recursive DFS approach aligns naturally with the problem structure and is more efficient overall. Ultimately, we chose the optimized DFS approach as the most effective strategy for solving this problem. This method avoids unnecessary string construction by performing lexicographical comparisons directly during traversal, significantly improving efficiency. Compared to the brute force method, the optimized DFS is both faster and more memory efficient, making it well suited for deep or large trees. Additionally, it is simpler to implement and debug compared to iterative alternatives, which would add complexity without major advantages. When comparing DFS and BFS, DFS stands out as the better choice here due to its natural alignment with backtracking and its lower memory requirements for handling narrow but deep trees. While BFS remains valid, it is less practical for trees with significant width. In conclusion, the optimized DFS approach strikes the best balance between simplicity, efficiency, and scalability, making it the optimal choice for this problem. In this problem, you're given a binary tree where each node contains a lowercase English letter, and your task is to find the lexicographically smallest string that starts at a leaf node and ends at the root. A leaf node is simply a node with no children, while a root-to-leaf path is the sequence of nodes from the root down to a leaf. However, since we need a string from the leaf back to the root, we'll essentially reverse the path during traversal. To approach this problem, we can use some key insights. First, we'll traverse the tree and maintain the path in reverse order as we backtrack. Second, since we're comparing strings lexicographically, we'll keep a global variable to store the smallest string found so far. Recursive depth-first search, or DFS, is particularly well suited for this task because it allows us to explore all paths systematically. To make our algorithm efficient, we can also use pruning. If a current path is already lexicographically larger than the smallest string found so far, we can skip further exploration down that path. These observations will guide us in designing the algorithm. To implement the algorithm, we can break it into two main parts, the base case and the recursive case. In the base case, if the current node is null, we simply return, as there's no valid path to explore. If the node is a leaf, we construct the string by reversing the path collected so far and compare it with the smallest string we've encountered. For the recursive case, we add the current node's character to the path, then make recursive calls to explore the left and right children. After processing both children, we backtrack by removing the current node's character from the path. This backtracking step is critical because it ensures that the path remains accurate as we traverse other parts of the tree. For implementation, we use a list to store the current path since lists allow efficient appending and backtracking. We also use a global variable, smallest_string, to store the smallest string found so far. It's important to handle edge cases, such as when the tree is empty or contains only one node, and also ensure that paths of different lengths are compared correctly. One of the key insights is to store the path in reverse order as we traverse the tree. This simplifies the process of comparing strings because the path already represents the string from leaf to root. Pruning is another important optimization. If the current path exceeds the smallest string found so far in lexicographical order, we can terminate exploration down that path early. Backtracking is essential to ensure memory-efficient traversal, as it prevents us from creating unnecessary copies of the path. To implement this, we use a list as a stack to store the current path during the DFS traversal. By appending characters as we descend and removing them as we backtrack, the list dynamically represents the path at any point in the recursion. We also use a global variable to track the smallest string encountered so far. This avoids the need to recompute the smallest string repeatedly. Here's a snippet of pseudocode to illustrate the algorithm. In the DFS function, we first check if the current node is null and return if it is. Otherwise, we add the node's character to the path. If we've reached a leaf node, we construct the string by reversing the path, then compare it with the smallest string found so far and update the smallest string if necessary. The DFS function then continues by making recursive calls to explore the left and right children. After these calls, we backtrack by removing the current node's character from the path, ensuring that the path remains accurate for other branches of the tree. The main function, smallest_from_leaf, initializes the global variable smallest_string with a very high lexicographical value to ensure that any valid path will replace it. If the tree is empty, the function simply returns an empty string. Otherwise, it calls the DFS function starting from the root, with an empty list representing the initial path. Once the traversal is complete, the global variable will contain the lexicographically smallest string, which is returned as the result. In terms of time complexity, each node in the tree is visited exactly once. Constructing the string from the path takes time proportional to the height of the tree, so the total time complexity is O(n*h), where n is the number of nodes and h is the height. This ensures that the algorithm is efficient even for larger trees. The space complexity of the algorithm is primarily determined by the recursion stack and the space used to store the path. Both of these are proportional to the height of the tree, so the total space complexity is O(h). To optimize further, we can prune paths that cannot lead to smaller strings, saving unnecessary computation. Using a mutable list for the smallest string avoids frequent string construction, which can be costly. Backtracking ensures that the path is memory efficient, as characters are added and removed dynamically without creating additional copies. To see how the algorithm works in practice, consider the example of a binary tree with the root node labeled B, its left child labeled A, and its right child labeled D. The left child of A is labeled C, and the right child of A is labeled E. This tree allows us to explore multiple paths and compare their corresponding strings to determine the smallest one. We start at the root node labeled B, adding it to the path. From there, we move to the left child, A, and then to its left child, C, which is a leaf node. The path at this point is B, A, C, and the corresponding string is CBA after reversing the path. Backtracking to A, we now explore its right child, E, which is also a leaf node. The path here is B, A, E, and the string is EBA. Returning to the root, we then explore the right child, D, reaching the path, B, D. Comparing all strings, we find that CBA is lexicographically smaller than both EBA and D. Thus, the result for this tree is CBA. This example demonstrates how the algorithm systematically explores all paths, efficiently compares strings, and uses pruning and backtracking to optimize the traversal process. The given code solves the problem of finding the lexicographically smallest string starting from a leaf node and ending at the root of a binary tree. Each node in the tree contains a value between 0 and 25, mapping to the lowercase English letters A to Z. ###explanation. 1. Function definition. The smallest from leaf method takes the root of the binary tree as input. This method uses a depth-first search (DFS) approach to traverse the tree and build strings from leaf nodes back to the root. 2. DFS helper function. The DFS function is defined to recursively traverse the tree. It takes the current node and the constructed path string as arguments. The path is built by prepending the character corresponding to the current node's value, CHR, 97 plus node.val. 3. Leaf node check. If the current node is a leaf, i.e., it has no left or right children, the constructed path is compared with the smallest string found so far. If the smallest variable is none or the current path is lexicographically smaller, the smallest variable is updated. 4. Recursive traversal. The DFS continues recursively for the left and right children of the current node, carrying the updated path string. 5. Result. After the DFS traversal completes, the smallest variable contains the desired string, which is returned as the result. Edge cases. If the tree has only one node, the result is the character corresponding to that node's value. If the tree is unbalanced, the algorithm still works as it explores all paths from leaves to the root. The algorithm handles trees with duplicate values correctly since it compares full strings lexicographically. This approach ensures that all paths are explored, and the lexicographically smallest string is found efficiently. The recursive DFS traversal is straightforward and ensures correctness by constructing strings in a bottom-up manner, from leaf to root. Here, we start with the Java implementation of the solution. The DFS method is a helper function designed to perform a depth-first traversal of the binary tree. The first thing to notice is that if the current node is null, we simply return to avoid further processing. Next, we prepend the character corresponding to the node's value to the path. This is achieved by converting the node's value into a character using char, a plus node.val. This ensures that the path reflects the string representation of the values as characters. Now, if the current node is a leaf, meaning both its left and right children are null, we convert the path to a string and compare it to the smallest string recorded so far. If it's smaller or if no smallest string has been recorded yet, we update the smallest array with the current path. For non-leaf nodes, we recursively call the DFS method for both the left and right subtrees. Finally, the method includes a backtracking step where we remove the character we just added to the path. This ensures that the path remains accurate for other recursive calls higher up in the tree. Now, the smallest from leaf method acts as the entry point for the solution. It initializes an array called smallest to store the smallest string found during traversal. Using an array here allows us to update its value inside the recursive calls since arrays are passed by reference in Java. The DFS helper method is then invoked with the root node, an empty string builder to build the paths, and the smallest array. Once the DFS traversal is complete, the method returns the smallest string stored in the array. Finally, we have the treeNode class, which defines the structure of the binary tree nodes. Each node contains an integer value and pointers to its left and right children. This setup ensures that we can build and navigate the binary tree as required for the problem. Let's start by examining a simple binary tree example. The root of this tree is the node labeled B, which has a value of 1. It has two children, the left child A, with a value of 0, and the right child D, with a value of 3. Our goal is to find the smallest string that starts from a leaf and ends at the root. We'll accomplish this using depth-first search, or DFS. First, we initialize the path as an empty string and set smallest to none to keep track of the smallest string we encounter. Beginning at the root node B, we prepend its character, B, to the path, resulting in path equals B. Next, we explore the left child, A. Prepending it to the path gives us path equals AB. Since A is a leaf node, we compare this string with smallest. Because smallest is currently none, we update it to AB. We then return to the root node and proceed to explore the right child, D. Prepending D to the path results in path equals DB. Node D is also a leaf, so we compare DB with smallest. Since AB is lexicographically smaller than DB, we keep smallest as AB. Now that both children have been explored, we return to the root node. DFS is complete, and the smallest string we've found is AB. Thus, the output for this tree is AB. Turning to a larger and more complex tree, this time the root is C, with a value of 2. It has two children, B with a value of 1 and A with a value of 0. Node B itself has two children, D with a value of 3 and E with a value of 4. Node A has a single right child, G, with a value of 6. Again, we use DFS to find the smallest string starting from a leaf. Starting at the root node C, we initialize the path as an empty string and smallest as none. Prepending C to the path gives us path equals C. Next, we explore the left child of C, which is B. Prepending B to the path results in path equals BC. From here, we first visit the left child of B, which is D. Prepending D gives us path equals DBC. Since D is a leaf, we compare DBC with smallest and set smallest to DBC. Returning to B, we now explore its right child, E. Prepending E gives us path equals EBC. Node E is also a leaf, so we compare EBC with smallest. Since DBC is lexicographically smaller than EBC, smallest remains DBC. Returning to the root node C, we now explore its right child, A. Prepending it to the path results in path equals AC. From here, we move to the right child of A, which is G. Prepending G gives us path equals GAC. Node G is a leaf, so we compare GAC with smallest. Since DBC is still smaller, we keep smallest as DBC. With all paths explored, DFS is now complete, and the final result is DBC. Finally, let's examine the simplest case, a tree with only a single node. Here, the tree consists of just the root node A, which has a value of 0. In this case, the DFS begins and ends at the root, as it is also a leaf node. We initialize the path as an empty string and smallest as none. Prepending it to the path gives us path equals A. Since A is a leaf, we compare A with smallest. Since smallest is initially none, we update it to A. With no other nodes to explore, DFS completes, and the result is A. This demonstrates how the solution handles even the simplest tree structures efficiently. The time complexity of our solution is O, n, where n is the number of nodes in the binary tree. Let's break this down step by step. First, the algorithm performs a depth-first search, or DFS, to traverse each node in the tree exactly once. Because we visit every node only one time, the traversal alone has a time complexity directly proportional to the number of nodes, which is O, n. Additionally, for each node, we perform a string operation. Specifically, we prepend the character associated with the node's value to the current path string. Prepending a character has a time complexity of O, k, where k is the length of the string. In the worst-case scenario of a completely skewed tree, the string length could grow to match the height of the tree, h, which can be as large as n. However, when summed over all nodes, these string operations still contribute only O, n, in total. Combining these factors, the overall time complexity of the algorithm remains O, n. Now let's analyze the space complexity, which is O, h, where h is the height of the binary tree. The first contributor to space usage is the call stack, since the algorithm uses recursion to traverse the tree. In the worst case, such as a completely skewed tree, the recursion stack can grow to a depth of h, which matches the height of the tree. For a balanced binary tree, h would be log n, while for a skewed tree, h could be as large as n. This means the space required for the call stack is O, h. The second contributor is the storage for path strings constructed during the traversal. At any point, the memory required for a path string is proportional to the height of the tree, h. Since we only maintain one path string at a time in memory, this also adds O, h, to the space usage. Therefore, the total space complexity is determined by these two factors, resulting in O, h. Let's compare this approach to a brute force method. In a naive solution, we might generate all possible paths from leaf to root and then sort them to find the smallest string. For a binary tree of height h, this would involve generating O, 2 to the power of h, paths. Sorting these paths would add a time complexity of O, 2 to the power of h asterisk k log, 2 to the power of h, where k is the average path length. In contrast, the DFS approach avoids generating all paths and computes the smallest string directly during the traversal. This optimization keeps the time complexity at O, n, and significantly reduces space usage. Analyzing the best, average, and worst cases, the time complexity remains O, n, throughout, as every node is still visited once. However, space complexity depends on the tree's height. For balanced trees, where h is log n, the space complexity is O, log n. For skewed trees, where h equals n, it increases to O, n. Overall, this DFS approach is optimal for the problem, balancing both time and space efficiency. Here, we highlight some common mistakes to watch out for when solving this problem. First, failing to handle edge cases like an empty tree or a single-node tree can lead to runtime errors. For example, your algorithm might assume child nodes exist without verifying, which can cause it to break. Testing edge cases is essential to ensure robustness. Next, recomputing values for each recursive call is another pitfall. If your solution repeatedly calculates the same results for already visited nodes, it becomes inefficient. Using memoization or switching to an iterative traversal can significantly optimize performance. Another frequent error is confusing root-to-leaf traversal with leaf-to-root traversal. These require different logic, so understanding the direction specified in the problem is crucial. Lastly, string concatenation errors are common. Some solutions may incorrectly concatenate integers or forget to reverse the string as required. Always validate your output against the expected format to avoid subtle mistakes. Now, let's consider the importance of constraints and some key interview insights. Ignoring input size constraints, such as the maximum depth of the tree or the number of nodes, can lead to inefficient solutions. For instance, a solution with O, n superscript 2 complexity might not perform well under these constraints, so optimizing for O, n is often necessary. Recognizing patterns is another critical skill in tree problems. Techniques like DFS, BFS, or backtracking frequently appear, and being able to identify when to apply them will make solving variations much easier. Additionally, if you use recursion, always explore whether memoization or iterative methods could enhance performance. In interviews, testing your logic with small, simple cases is a must. This helps identify edge cases early. Finally, be prepared to discuss trade-offs. For example, you might choose DFS for its simplicity, but it can be memory-intensive in deeply nested trees. Being able to justify your approach is a valuable skill. Let's explore some related problems that share similar concepts or techniques. First is binary tree paths on LeetCode, which asks you to generate all root-to-leaf paths as strings. This is a great example of constructing paths through traversal. Next, pathsum involves checking if a root-to-leaf path matches a given sum, introducing a numerical aspect to tree traversal. Some root-to-leaf numbers builds on this idea but requires computing the total sum of all root-to-leaf numbers. Finally, the current problem, smallest string starting from leaf, focuses on finding the lexicographically smallest string by traversing leaf-to-root paths. Studying these problems can deepen your understanding of tree traversal and path construction techniques, as well as help you recognize patterns across different variations. Lastly, let's discuss alternative approaches to solving this problem and their trade-offs. Depth-first search, or DFS, is often easier to implement recursively, but it can lead to stack overflow in deeply nested trees if recursion depth isn't managed carefully. Breadth-first search, or BFS, avoids recursion issues by using a queue, though it comes at the cost of higher memory usage. Backtracking is another powerful approach, especially useful when constructing paths dynamically. However, it requires careful state management to avoid introducing errors. Finally, memoization is invaluable for speeding up solutions by storing results of sub-problems, but it increases memory requirements. Understanding these trade-offs will help you choose the most appropriate approach based on the problem constraints and your specific needs. To wrap up, we reviewed the smallest string starting from leaf problem, explored traversal and optimization techniques, and discussed complexities. Remember to keep practicing tree-based problems to master traversal patterns. Thank you for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!